right, hello. Yeah, okay, it works. Hello, so my name is Andrzej Rybczak, and today we're going to talk about profunctors and data accessors and how do they relate to each other. And okay. All right, so first, the motivation, right? Why do we care? So the problem is that Haskell doesn't have user-friendly, available out-of-the-box set of features for modification and access of nested data structures, right? Haskell is a functional language. Functional languages encourage you to use smaller functions to build larger ones by composition, but the built-in record syntax is clunky to use and doesn't compose very well. So the solution was found to be lenses, right? And other things, such as adapters, otherwise known as ISOs, prisms, traversals, and so on. And so the whole family of this is known as optics. So we'll be talking about optics from now on. And there are multiple encodings of these, right? So there is a concrete encoding, which is usually found in tutorials. It's basically any optic is encoded as a pair of functions usually, and the encoding is easy to understand. That's why it's usually included in tutorials. But the problem with concrete encodings is that they don't compose well. So, for example, if you think about that, what is the composition of a lens and a prism? So I didn't cover yet what is a prism, but we'll get to that. But it is neither lens nor a prism, so it's not clear what it is. And also, there is a lot of they can compose in various ways, right? There is a lot of combinations, so this doesn't really work well. There is Varlar-Hoven encoding, which is used in the lens library, and these encodings are so that's a big advantage of this encoding. You can use the usual function composition to compose them, and lenses and traversals don't require anything other than the base library, which is the Edward Quet says that it is a setting point of the lens library. Although it probably wouldn't matter much if the lens library didn't have 20 dependencies, but but yeah. The types are a bit convoluted. Like if you are new to lenses and new to optics, and you try to read the documentation of lens library, you will be quickly overwhelmed with types. And the hierarchy of optics is not clear from the types. It's documented pretty well, but it is not clear what kind of optics you can plug into what functions that view or modify types. And then there is the profunctor encoding, which is used by one library I know that it uses is PureScript profunctor lenses library. I don't know if there is any Haskell library that uses profunctor encoding. And lenses in profunctor encoding are composable. They do require profunctors. Types are still somewhat convoluted, but they are simpler, in my opinion, than the Varlar-Hoven representation. And the big plus, I think, is that hierarchy of optics is clear from the types. All right, so the idea is that I'm going to present the optics in a concrete encoding. Then we'll go to profunctors, and then we'll go to encoding of these optics as profunctors, like in a profunctor encoding. All right, so let's start with an adapter, right? It's otherwise known as ISO in the lens library. It's named like that, and it provides a way to convert back and forth between the types, between two types. Usually an isomorphism, although we don't enforce it here, right? So, and one thing to notice is that there are 4 type parameters, right? And you can think of it that if we are talking about the conversion back and forth between types that are not parameterized by any type parameter, then usually A equals B and S equals T, right? So then The case is a bit simplified. But for example, we need four type parameters, for example, for sum A, right? That's a new type wrapper for that provides a monoid instance, specific monoid instance. So the next type of object is a lens, right? And a lens is a pair of two functions, essentially, a getter and a setter, or updater. And as you can see, a lens is quite similar to an adapter. Like, essentially, adapter is a lens that doesn't take s, right? In here, update function takes an s, b produces t. Here, it doesn't take s, so you can think of an adapter as a lens that ignores the s. Okay, so basically, a lens allows us to view a value contained within a larger data structure and update the specific part of it, right? That's what the view function is, that we take a larger data structure and then we extract some smaller part. And that the update function takes a large data structure, the smaller value, and updates it and produces a new value, right? So here we have an example. The first lens basically updates. We can focus on a first coordinate of a pair, right, and the second appropriately. So, and the lenses deal with product types. So the next thing is a prism. And a prism is a dual concept to lens in that it allows us to match on a value possibly contained within a larger data structure, right? So lens always matches, but a prism doesn't have to. It possibly matches. And it also allows us to build the data structure back from a specific value. And it deals with sum types, right? So it's a dual product dual concept to a lens, right? And here we have an example, like a left is a prism that matches on the left side of an ether and can build back ether by just simply applying the left constructor. And right is a prism that matches on the right side of an ether and can build ether from a value by simply applying the right constructor. Another one is a traversal. So here I'm cheating a little bit because this is not actually a concrete representation of a traversal. This is the var-Larhoven encoding of a traversal. But the concrete representation of a traversal is somewhat hard to understand. I think this is better. It captures the concept better because basically the traversal is a generalization of traverse from data traversable, right? So if you have traverse, like traverse is basically a traversal from A to B, A, B, T, A to TB, right? And an example is the traversal that traverses both coordinates of a pair, assuming the types of a pair are the same. And it allows us to match and or modify multiple values possibly contained within a larger data structure in a predefined order, right? So as you can see, it has some characteristics of a lens, and it also has some characteristics of a prism. And it also allows us to apply fx specific to f, right? And it deals with a sequence of values of any type. All right, so these are the four optics we'll be talking about. And how do these optics relate to each other, right? So it turns out that the relation is as follows. So every adapter is a lens, every adapter is a prism, every lens is a traversal, and every prism is a traversal. And it is somewhat clear, like for example, I showed you the relation between adapter and a lens. That adapter was basically a lens that was ignoring one of the arguments. But for the other ones, it's not necessarily clear. And how can we see that? How can we see that that hierarchy? And also, how can we make these optics composable with each other, right? Because potentially, if we have in a real world, in a real scenario, we have just a bunch of lenses, a bunch of prisms, a bunch of traversals, a real data structure, like for example, a list of pairs of where the first coordinate is an ether char int, and the second coordinate is a string, and we want to just traverse the whole list and update the first coordinate of a pair if it is a right constructor, right? So how can we do that? So that's where profunctors come in. And the profunctor is basically represented by a type class in Haskell. But in order to arrive at the definition and have some intuition about that, we need to backtrack a little bit. So let's talk about covariant functors, right? So it's a type class we all know and appreciate. It is represented. So covariant functor in Haskell is represented by a functor type class, right? So basically, intuitively, f of a will output values of type A in a context specific to f, right? And it allows, and fmap function allows us to map over f to change the type of its output. And we say that argument a in fa is covariant. So basically, if we're talking about the functor, we're talking about something that outputs things in some specific context. And examples are plenty, right? This identity functor may be functor. IO is also a functor, and iter a, if a is a specific type, is also a functor. Then we have a contravariant functors, and they are significantly less popular, right? But they are represented by a contravariant type class, which is very similar to a functor type class. We have a contramap function, but notice that the arrow in the first argument is reversed, right? So fmap was taking a function from A to B, and contramap is taking a function from B to A. And what is that, right? What does that mean? But intuitively, f of a will take values of type A as an input in a context specific to f. And contramap allows us to map over f to change the type of its input, right? So covariant functors talk about, if it comes to covariant functors, we can think of something that produces things. And if it comes to contravariant functors, we can think of something that consumes things. And an example is a predicate, right? A predicate is basically a function that takes some value and produces a Boolean, whether the predicate is gives us true or false. And given a predicate that takes an int that checks whether this int is even, we can construct a predicate that takes a string by contramapping length over the predicate is even, right? We basically contramap length over the input. So, and we get a predicate that succeeds whether the length of the string is even. All right, so now given these two things, we can define what a profunctor is. So profunctor basically glues these two concepts together. So a profunctor, an instance of a profunctor is a type PAB, where the first argument is contravariant and the second argument is covariant, right? And intuitively, it is a transformer that consumes values of type A and produces values of type B. And the canonical example of a profunctor is a function arrow, right? Because function arrows have input and an output, and we can map over an input and an output. A more interesting example from foldle package is the fold data type, which represents the left fold, right? So we have some internal state. We have a step function. We have the initial state, and we have the extraction function that extracts the final value from the internal state. And it is a profunctor because we can contramap over all the inputs, and then we can map over the final output. So, okay, let's talk about functors that went pro. So here are the three new type definitions, which are pretty similar. And can anyone tell me which of the above are profunctors? Any guesses?
First two, third? All three?
Yeah, all of them are. So all of them have the profunctor instance, and as you can see, the form of all of these instances is pretty similar, right? And this can actually be generalized to any functor f. So we introduce a new type star that takes f a b, and basically it is a function from a to f of b. And if f is a functor, then star f is a profunctor. So that essentially means that we can inject any functor into a space of profunctors, right? And the star is, if you're wondering about the name, the star is basically a borrowed convention from mathematics, where if you have two spaces and one is somewhat smaller than the other in the sense that there is an injection from the smaller ones into a bigger one, then the injection is usually denoted as a star, so that if you have a point from the smaller space, then the point with a star is a point from the bigger space. All right, so now we've defined profunctors. Now let's talk about Cartesian profunctors. So a Cartesian profunctor is intuitively, it can be extended with additional context in the form of a pair, right? So it deals with product types. Now you can think like that you should be thinking about there is some connection with lenses, right? Because lenses dealt with product types, and Cartesian profunctors also deal with product types. So the Cartesian profunctor has two functions, the first and second. They are symmetrical. They can be defined in terms of each other. So we'll focus on the first one basically. So the function arrow is a Cartesian profunctor because we just map over the first coordinate of a pair, and star f is also a Cartesian profunctor because we do the same, except then we just need to do some additional plumbing by moving the f outside of the type, right, from the to the outside of the pair. Okay, so we had Cartesian profunctors. Now we have co-Cartesian profunctors, which are the dual concept, and they deal with. So intuitively, a profunctor is co-Cartesian if it can be extended to act on one part of the sum type while leaving the other part alone, right? So Cartesian profunctors deal with product types. Co-Cartesian profunctors deal with sum types. And again, there is a left and right method. They are, again, symmetrical. And basically, and also, again, the function arrow and star f are both Cartesian profunctors. And with the function arrow case, we just map over the left side. And in the star f case, we actually require f to be an applicative because we need to inject the right value into a functor, and we need pure for that. And left, we just and for the left side, we just execute f and then inject f left into a functor so that it type checks. All right, so that slide is actually a bit sketchy. Basically there is some circularity here, but this is essentially a way to So again, there is an instance for a function arrow and for star f, and they are very simple, right? We just for the function arrow, we take the f to be identity and type the types are the type match, and here we just unwrap and unwrap the star. Unwrap star has a function a to f of b, so we just apply it to f to t, and then we rewrap it, right? Because this is exactly what we want to have. All right, so finally, like after all of this preparation, we can talk about what a profunctor optic is. So a profunctor optic is basically a transformation of profunctors. So an optic in the profunctor encoding is represented by the type synonym optic PABST, which is basically a profunctor transformation. We take PAB and we want to get PST. And the previously mentioned optics in the profunctor encoding are as follows, right? So an adapter is a profunctor transformation that works for any profunctor. A lens is a profunctor transformation that works for any Cartesian profunctor. A prism is a profunctor transformation that works for any co-Cartesian profunctor. And a traversal is a profunctor transformation that works for any Cartesian, co-Cartesian profunctor, and we also want this wonder class. Okay, now let's prove that the equivalence. All right, so we have the adapter type class. I omitted the names this time. So an adapter AB is a profunctor. Like this, the definition of the D map is fairly straightforward. And now the conversions for all of the optics are very similar. So let's check how it works, because I think that's a pretty crucial thing. So if we want to convert from the concrete representation into a profunctor representation, right? We get an adapter, and adapter P is something that takes PAB and converts it into PST, right? So we get PAB, and we have the from function and the to function, right? But that's exactly what, and the from function has type S to A, and to function has a type B to T, right? And the first mapping is contra mapping, right? So the arguments are reversed, and the second, basically this has exactly the types that we want. So we just demap. And if we want to convert back from the profunctor representation to the concrete representation, we use the fact that adapter AB is a profunctor, and we construct a trivial adapter, and then we transform it with our profunctor transformation, right? So we pass adapter AB to L, and L transforms it into adapter AB ST, which has the type we want. So for lenses, okay, let's how much time do I have? With questions? Okay, all right. Okay, so this is just type Tetris. So let's keep that. Let's focus on the conversions. So here, this is the same pattern, right? We have a view function, an update function. We have PAB. We want to have PST. But note that the view function is converts S to A, so there is no issue here. This is the same thing as in previous case. But the update function takes B to T, but it also wants S. And if we are demapping, here we wouldn't have S. So we actually need to make use of the Cartesian, of the fact that we are talking about Cartesian profunctors here. And we extend PAB. We extend the context the PAB operates in by S. So now we have S here, and then we can apply the update function. And here we just leave the S alone. And the other way, we do it the same thing as with adapters. We construct a trivial lens, and then we apply the transformation to it, right? Lens is a Cartesian profunctor, so this transformation works on it. And for a prism, it's the same thing. It's exactly the same, except when we do the transformation from we transform from the concrete representation to the profunctor representation. We extend the profunctor to act on the sum types, right? That's why we need that's why prism P works on co-Cartesian profunctors. We need to call this right function to extend it in order to apply which function match, right? Yeah, we need to apply the match function. Like we need to extend it in order to apply the match function. And again, here we construct a trivial prism and let the transformation do its thing. And the traversal case is actually the easiest, I think. So here the conversion from the traversal to a traversal in a profunctor form is basically wonder, because that's how the wonder was defined. And when we convert from traversal in a profunctor form to a traversal in van Laarhoven form, we instantiate the profunctor to star f when f is applicative, and we just wrap and unwrap it. All right, so that's for the theory. Now let's do some demonstration that it actually works, because yeah. All right, so I have the everything that was here. Do you actually see that? Okay.
Can you invert the colors?
Okay, so let me actually. I can't. Let me actually just make the font bigger. Is that better? Yeah, okay. All right, so as you can see, it doesn't require anything. The file doesn't require anything, just the const functor identifying functor monoid and the prelude that has 300 lines. Yeah, 300 lines. All right, so now we have. Let's talk about the lens that focuses on the first coordinate of a pair, right? How do we use it? So how can we use it to, for example, apply, let's say that the A is a string and we want to apply concatenate with an exclamation mark. So actually, if you apply, just apply the function, then GHC picks the profunctor to be a function arrow, and everything collapses into a function that just modifies the pair. So, okay, without T. Yeah, so it works. So it just works. And for viewing, there we have this view function, viewL. We basically we instantiate the optic with a profunctor where P is a star, and then we take F to be a const functor, right? So we have this transformation, and know that this transformation is basically a function from A to star const AB, right? So what we do is just inject the value that we want to take out as a result into a const functor. Then we apply the transformation, but we are not interested in what it actually does. And then we just take the value we injected into the const functor at the end. So like this, right? And then if it comes to composition, the composition, like if we want to, for example, modify the left, like if we want to, for example, add 1 to the left coordinate of the first to the left side of the first coordinate of a pair. Then we can just do that, right? And if we do, that would be right, then we get the original value back. All right. Right, the first dot left. Yeah, so it combines the constraints, and you get basically a traversal. All right, there is actually a preview, also a preview function, because VUL works for lenses. It doesn't work for prisms. So for prisms, we actually need you need a preview function, and preview function is very similar to the view function, except that we also use the first new type, because the const. So if you think about the const functor, here is where is the applicative? Right, in the applicative, the m in the const m needs to be a monoid, right? Because how do we combine the values if you apply, right, to applicative functions, or how do you if you have a pure action, then how do you inject it into a functor? You need to use empty then. So that's why we use additionally the first, and then we can what we can do preview left. And it gives us nothing, right? But then it gives us just a. All right, and also, okay. So if it comes to traversing, so let's look at the sample one. Sample one is a list of either int, char, and string, and what we want to do is, let's say that we want to traverse the list and enter the first coordinate, and then left side, and we want to maybe by 10. Yeah, so that this sample, right? So that just works. Like all of these things just compose. If you look at the type, yeah, so that's traversal. And okay, one more example. So we have a sample 2, which is a list of either a pair of int and char. And what we would like to do, let's say that we want to get the sum of all the ints on the list, right? So we can traverse, then enter the left, and then we also have both, right? This traversal that traverses both coordinates of a pair, and we want to get the value, but we want the sum, right? So we also but we have ints, and that works because of the monoid, right? The monoid in const functor, right? Of VUL uses const functor, and sum is a monoid, so it just goes through the list and collects all of these ints, but we've applied sum constructor and then combines it using mapend. So I think that's it. Okay, I have one more slide actually. Okay, the summary. So that was based on the Profunctor Optics Modular Data Accessors paper. So you can look at this if you want some more details, and also the glossary post by Oleg. And the slides and code will be available on my GitHub. there is a repo for that, although it's not, doesn't have the latest version because my Git broke. But yeah, I will update it on Sunday or something. So yeah, that's it. Thank you.
Cool, I think we've got time for some questions, if anyone has any.
So are you then basically telling us that this makes lenses comprehensible and that we should try them now? Or,
Yeah.
For those of us who've been holding off, going, oh God, what do you think?
Yeah. So basically, like if you think I think this gives a lot of more insight than what is in the lens library, because if you think like there was some post or there was some explanation by Edward Kmet on Reddit about the various kinds of optics, and he said that these two optics need contravariant, lenses and traversal need functor and applicative, and then prisms need profunctors. But yeah, so it's just like it's all over the place, and you can see exactly how it relates to things. But here you have like yeah, the types are not very nice, but there is a clear hierarchy, right? Like you have, it's the same shape, it's just different constraints. So I think like that made me this encoding made me understand lenses basically, like the optics, right?
Can you show us some error messages you get when you try to compose lenses in the film?
All right. I'm not sure. Do you have anything in mind?
So for instance, here, if you replace a left by a second traverse, it should just.
Aha. Okay. Okay. Maybe. Okay.
Or maybe which. Okay.
Let's try to,
Okay.
to view instead of preview a prism.
Yeah. Right. Okay. Yeah. You will get that error about lack of monoid instance. Wait. Oh, maybe not then.
Maybe you need to give the one a type.
Yeah.
All right. Yeah. Yeah. Yes. Well. Yeah, so I guess that's one case where it's not clear if you don't know that if you don't know that it uses the view L uses const functor, and that const functor requires monoid.
At least it's way less overwhelming.
Yeah, like I am not actually familiar with the error messages from the lens library because I don't use it much.
Thank you.
Any other questions?
So is it on HaskellX, and why not?
Right. So that was the paper does some implementation. What I did was just put what was in the paper mostly and what was in the Profunctor lens library for pure script. I think there is like as I mentioned, I'm not actually sure if there exists an implementation of lenses in a Profunctor form for Haskell. And it might just be by inertia, right? Like the lens library has so many things that probably that's if someone wanted to start it, then maybe it feels overwhelmed to provide an alternative. But I'm not sure actually.
I have a question which might be very general. I mean, this is Profunctor in the Hask category.
Yeah.
And is there a general encoding for parameterized by the category of that you are choosing?
Right. So I actually
like a real Profunctor. A real Profunctor, it doesn't exist. I mean, it's not linked to one particular category.
Yeah. So all of these things come from category theory, right? The proper profunctors, Cartesian profunctors, co-Cartesian profunctors, like I have all of it. But I am no category theory expert. Like I don't know a lot about these things. So like that just shows you that you don't have to actually know category theory to have a good understanding of how these things work in Haskell.
Yeah, because a Profunctor in general it generalizes the home set in a.
Yeah,
it
probably.
behaves like a home set. I mean, if you know about function, you know about Profunctors in a way.
Yeah, I guess. Yeah, but generally, if in yeah, but generally in Haskell, if you talk about all of these things, then the category is implied to be Hask, right? And yeah.
Any more questions? Yeah.
So, given that a profunctor is kind of like a thing where you can do something to the input or do something to the output, it seems like machines or pipes might be profunctors, and I'm not sure if that is the case, but A, do you think they are, and B, do you think what would the optics applied to those profunctors look like?
Right. So I'm actually not sure. So if you like the thing is that profunctors, I know that profunctors have a relation to arrows. I actually wanted to add some slide about that, but then it was too much information already. But I don't actually know about pipes. How do these relate to profunctors? I only checked the relation to optics.
Maybe a minor remark to that. I mean, so generally in Haskell, if your data is covariant, then it's a functor. That's and I mean, basically the only thing that can go wrong when in that thing is it might be contravariant. And so what happens then is basically that it's a contravariant functor, and the thing is, profunctor basically just combines those two notions. And so if you have a profunctor, or this basically means that everything is a profunctor. I mean, of course, it doesn't apply to I/O, and if you have too many, like if you have more than two you of course have many different possible instances of those things, but at least I would assume that basically everything except I/O that you regularly deal with is a profunctor or many profunctors. So yeah.
What is the question?
No, I just wanted to because there was this previous question about the pipe, and
okay.
so basically I would say the answer generally is yes. I would say everything is a profunctor, basically. Well, yeah.
I don't have much experience with PureScript, but do you know if this profunctor encoding is a popular library in PureScript? Is it used a lot? And is there any feedback in the PureScript community about these different lens encodings?
I don't know. So I know that Edward Kmet actually advocated PureScript guys to go with the Profunctor encoding for the Lens library. So basically, he said that for the Profunctor it was fine because they were starting from scratch, but not for PureScript it was fine because they were starting from scratch, but for Haskell that it's a much harder sell. Although I didn't exactly I don't exactly know what he meant by that. Maybe just because the Lens library is so comprehensive and it uses the var-larhoven encoding.
Maybe when Simon Payton Jones has already criticised the Lens library as being too complicated, and so introducing Profunctors as well might be even less popular. So, I don't know.
Cool. I think we've got time for just one more question.
Is there any difference compared to any difference in the runtime characteristics compared to the big old Lens library by Command?
I'm not sure. I mean, I am not going to make any claims about inlining because of the presentation we saw yesterday. But I suspect that it should inline, given that you apply enough inline pragmas. Yeah.
Okay, I think we'll wrap it up there. So let's thank the speaker once more. Cool. And